So I think I can start. It's already time. Can I start? Yeah. So first of all, I'd like to thank you for coming to the second lecture. And I'm Gisela da Silva. I am a visiting professor here at Biostatistics, and I'm from São Paulo, Brazil. And I'm going to be presenting the seminar, Same or Not Worse, Methods for Equivalence or Non-Inferiority Tests. Before I start, we are asked to disclose our relevant financial relationships with any commercial interest, and I don't have any relationship to disclose. Also, I would like to ask you, please, to fill out an evaluation and sign up, especially if you want the CME credits. So don't forget to fill out the evaluation and sign in, okay? At the end of the lecture, you can leave the evaluation at the table, on the table at the back. This is the outline of my talk today. I'm going to start with the introduction, and I'm going to present the same example that was used last month by Dr. Lode. So we're going to discuss a little bit the blood pressure example and I really want to discuss the error types with you. And then we're going to look at the second data example that is bone marrow transplant data. And then we are going to discuss the non-inferiority testing and the relation with confidence intervals. I'm going to discuss the equivalent testing with a third example, and then confidence intervals for equivalence testing, and a short discussion on power and sample size, and final comments. Okay, so this was an example used last month. And the main outcome of the study was drop in systolic blood pressure. So there were two groups, and they wanted to know if drug A reduces systolic blood pressure. And we had 36 patients treated with drug A and 36 patients treated with drug B. So we had the data, and all the descriptive analysis of this data and results was presented last month. So I'm not really going into the data. I just want to discuss the hypothesis of the test and the errors with you. That's my main objective here. So the null hypothesis was to, I would say that drug A is no better than placebo in reducing systolic blood pressure. That means placebo and drug A are equal. Or I can state the hypothesis saying that the mean reduction in treated target population equals the mean reduction with placebo. So drug A is equal to drug B. The alternative hypothesis would be drug A is better than the placebo for reducing the blood pressure. So those are the usual hypothesis testing hypothesis for testing for this test, the usual test procedure. And one nice way to understand a little bit better hypothesis testing is to think about the burden of proof. So the research really wants to show that the null hypothesis is false. So, and we are going to reject the null hypothesis if the data has stronger evidence against the null. If I don't have strong evidence against the null, I only can say that I cannot reject the null hypothesis. Though that's how we construct usually hypothesis tests. When we are testing hypotheses, I can make errors. And there are basically two types of errors, and all that was discussed last month, but I'm just reminding you. So if in the real situation the null hypothesis is true, and I reject the null hypothesis, I am making a mistake. It is an error, and we call that type 1 error. If the null hypothesis is true and I don't reject the null, I'm okay. This is the correct decision. If the real situation, the null hypothesis is false and I reject it, that's okay, correct decision. If the null is false and I don't reject, then I am also making an error. What those errors in our blood pressure example mean? The null hypothesis was the mean reduction of blood pressure when using drug A is equal to the mean reduction using placebo. And the alternative was that drug A is better than placebo for reducing the blood pressure. So the type 1 error is to reject the null when the null is true. The null hypothesis, the drugs are equal. So the error would be to conclude that drug A is better than placebo when it's not. That's my type 1 error. My type 2 error would be to conclude that the effect of drug A is equal to the placebos when in fact it is better. When I am really testing the hypothesis, I don't know, and there is no way of knowing if I am making an error or not. So I really don't know. However, I don't know if I'm making an error or not, but I know the probability that I'll be making a mistake or an error. So although I can't tell you for sure that I'm right or wrong, but I can tell you for sure that the probability that I'll be wrong would be 5%, for example. So alpha is the probability of type 1 error, is the probability of rejecting the null when the null is true. This gives us confidence in our decision. I don't know really. I know that I can make an error, but I know that the probability of making this error is small. And I can choose any alpha level. So alpha is the probability of making type 1 error, and I can choose any level we call level of significance. However, so I am controlling the type 1 error, but I also want a small probability of accepting the null when it's false, the type 2 error. The type 2 error is to accept the null or not reject the null when it's false. When the null is false, the treatments are not equal. That means drug A is better than placebo to reduce. If drug A is better than placebo, the reduction is different. And of course, if drug A is way better than placebo, the difference is going to be big, really large difference. So the probability of making a mistake is going to be small. But if drug A is better than placebo, but not that better, the probability of making this type 2 error is going to be bigger. So, bigger. So the type 2 error depends on the effect size. If the difference is really big, it's very unlikely that I will make an error. But if the difference is not so big, it might be more likely that I make an error. So for the type 2 error, we cannot really control it. What we do usually, we compute the probability of making a correct decision, and we call that power, and we compute the sample size, for example, so that we have at least that power that's desired. So that's how we do usually. So the results for the blood pressure, if you look at the slides from last month, the null hypothesis with this data was rejected. So there was evidence that that drug A was better than drug B, than placebo. So if you're curious about the data, you can go back to the last month's slides and see all the description, all the results. What I want to discuss with you now is the second example and compare with the blood pressure example. So this example is a bone marrow transplant study, and they wanted to compare peripheral blood stem cells, PBSC, or bone marrow cells. So we had patients. They needed bone marrow. They needed to go through a bone marrow transplant, and they can receive PBSC or bone marrow from their donors. And there are some advantages of PBSC. The collection is easier, and we observe faster engraftment. So those are good things about PBSC. However, the patients have more GVHD. I don't know how familiar you are with the transplant, but it's a disease that patients may have after they have a bone marrow transplant. So when they receive PBSC, they are more likely to have GVHD. So because of the GVHD problem, bone marrow, the bone marrow cells may be preferred. However, I'm gonna prefer bone marrow if the survival of patients are the same. So I want to now compare the two groups regarding survival, but I want to see if they are the same. I don't want to show that one is better than another. I want to show that one is not inferior to another. So it is different from the first example, where I had two groups and I wanted to know if one of the groups was better than the placebo. Here I have another one. I have two groups, and if BM is not inferior to PB, I'm going to prefer BM. So let's look here in this example at survival at 6 months. So I have a data set, a real data set of 911 patients, 503 received bone marrow, and 328 PB. We have information about survival, relapse of disease. So after the patients are transplanted, they can eventually die, or the disease, leukemia, usually can come back. So they relapse. And we have information about all the patients after 6 months. So let's look first at the proportion of patients that are alive at 6 months after the transplant. If we construct a usual hypothesis testing, my null hypothesis would be the proportion of alive patients at 6 months given bone marrow BM is equal to the proportion of alive patients given PBSC. That would be my new. My alternative would be the proportion of alive patients at 6 months given bone marrow is smaller than the proportion of patients that given PBSC. So those are the usual hypotheses. I can write them in this way, but that's exactly what I just said. And here, P for me is the proportion of alive patients, okay, given bone marrow and given PBSC. Let's look at the errors. When I state those hypotheses, my type 1 error would be to conclude that bone marrow is inferior to peripheral blood when they are equal. And the type 2 error to conclude that BM is equal to PB when it is inferior. And the test is constructed so that the probability of type 1 error is controlled. However, in this situation, the type 2 error is more problematic, because if we look at type 2, the type 2 error is to conclude that BM is equal to PB when it's worse. So I would be worried much more about this second error than the first one. But if I do a usual hypothesis testing, I'm going to control type 1 error. So what we do, I want to now control this error. So we switch the hypothesis. And this is what we call non-inferiority test. So my new hypothesis here is going to be the proportion of alive patients at 6 months given BM is smaller than the proportion of patients given PB. And I have to add this by some amount. So it's going to be smaller by some amount. And my alternative hypothesis is the proportion of patients given BM is not smaller than proportion of alive patients given PB. So we switch, and I have to write my hypothesis in this way. So P here is the probability of, or the proportion of alive patients. So the proportion of alive patients given BM is going to be smaller or equal to the proportion of alive patients given PB minus delta. So this is going to be smaller than this one. So this group is worse than this one. And my alternative would be this is not smaller than this, so this is greater than this. What is this delta here? This delta here is what we call non-inferiority margin. And it has to be defined prior to data analysis based on clinical judgment. And the interpretation of this delta is how close the new treatment must be to the standard to be considered non-inferior. So in our example, okay, if BM is not really equal to PB, but it, say, PB, the proportion of a live patient is 45% for bone marrow. If the PBSC is not 45, but it's 44.5, would that be okay to choose bone marrow because of GVHD? So that's kind of the interpretation of the delta. It's how close the new treatment must be to be considered non-inferior or to be considered to be used as a treatment for new patients. This is, of course, a critical issue, and there are many papers on the literature discussing how you should choose this delta, and I'm not going here into details, but sometimes it's not easy. So sometimes they state the hypothesis in terms of different quantities, so that it's easier to define the delta. So it's something critical, but it has to be defined. Well, when I am doing these non-inferiority tests, I still can make errors. And we define the type 1 and type 2 errors in the same way as the usual tests. So the type 1 error is to reject the null when the null is true. So type 1 error is always like that, to reject the null when the null is true. And the type 2 is to not reject the null when the null is false. So in our data now, my type 1 error would be to conclude that BM is not inferior to PBSC when it is in fact inferior. And type 2 error is to conclude that BM is inferior to PBSC when it's not. And I know the probability of type 1 error. So now I am controlling the probability of the worst error I can make in this example. I can state my hypothesis in this way. So this is the same as I had in the slides before. I just changed a little bit, but it's exactly the same. My null hypothesis is saying that this group is worse than this group, and my alternative hypothesis is saying that this group is not worse than this group by this amount delta. So that's what my hypotheses are saying. And there is a test statistics that you can compute, that you can use to test. So here it is. But for now, it's not important to know what this statistic is. I just want to show you that there is this formula, and we can compute this z-value. And for those that are used to the test for proportion, it's very similar to the other one, except for this delta, but this is not important. I just want to know that there is a formula. We compute the z here, and this is my rejection area. So if z computed using that formula is here, I reject the null. If z is here, I don't reject the null. And this value here depends on alpha, which is the probability of type 1 error. So that's how we do the non-inferiority test. There is a close relation between non-inferiority test and confidence interval. So an equivalent way of verifying non-inferiority is to compute what I am calling one-sided confidence interval. I'm going to just compute the lower bound of my confidence interval and compare this lower bound with minus delta. That's the idea. And I'm going to reject the null if my lower bound is, if minus delta is below the confidence bound. Let's understand this. So there is a formula here to compute this lower bound of my one-sided confidence interval. So I'm going to compute this lower bound of my one-sided confidence interval for the difference of the proportions. If you look at the formula, it is exactly the lower bound of the usual two-sided confidence interval, but with a different confidence coefficient. So the main important thing here is I can construct a usual confidence interval for the difference of proportions, and I only have to correct my confidence coefficient to do a non-inferiority test. That's the main idea of this. I compute my confidence interval, I correct my confidence coefficient, and then I can conclude or I can test the non-inferiority hypothesis. So let's see an example. Assume that I want to test two hypotheses, a non-inferiority test with 5% significance level. I will have to construct a 9% two-side confidence interval. So if I want a 5% significance level, my confidence interval must have a coefficient of confidence of 90% and not 95 as usually. And we are going to compare the lower bound of this confidence interval with the value minus delta. If minus delta is smaller than the lower bound, we reject the null. If it's not, we don't. So it's kind of hard to explain using words, but it's kind of easy to understand graphically. So I construct my interval for the difference of proportions. Here is my lower bound, my upper bound. Minus delta is here. I reject the null, and non-inferiority is stated. What does that mean? The difference in proportions are close enough to 0 so that I can consider that the treatments are equivalent. If I am in this situation, minus delta is here, so the difference of the two proportions may be greater than I would like to. So the treatment is not. It may be inferior, so non-inferiority is not stated. This treatment I want to test may be inferior than the standard treatment. So that's how we do usually the non-inferiority test. So let's go back to our example and see the results. So I had 911 patients. Here are the number of patients given bone marrow and PB. 57% of patients here in this group were alive at 6 months, and 61% of the patients here were alive at 6 months. Here I chose delta equal to 10% or 0.1. So here are my hypotheses. I computed the z-value using that formula I showed you. This is my critical value, so I compared this value with this one. It is smaller, so I don't have evidence to reject the null. The null hypothesis is not rejected. If you compute the p-value, the p-value is greater than 5%. Here I am using a 5% significance level, so I don't reject the null. If I look at the 9% confidence interval, we see that 10%, minus 10% is here. So the interval actually, I am in this situation. Exactly here. So I'm not here, I'm here, so I don't reject the null. And I cannot say that bone marrow is, I cannot say it's non-inferior. It may be inferior. Let's consider now the same data, but a different outcome. As I told you, when the patients receive a bone marrow transplant, they can die after a while, or sometimes they relapse. The disease comes back, and this is considered a treatment failure. So sometimes researchers are interested in the proportion of disease alive and disease-free patients. So here I'm looking now at the proportion of patients that are alive and without disease at 6 months. And I have the same 911 patients, and 52% of them received bone marrow, and 52% of them were alive and disease-free here without relapse at 6 months, and here 53% of the patients were alive and disease-free. If I choose the same delta equal to 10%, I can compute the z-value. I have the same critical value, 1.64. This is greater than this. This is my p-value. So this is in the rejection area. I reject the null. So I have the evidence that BM is no more than 10% worse than PS. It's wrong. It's wrong. PBSC. So if we look at the confidence interval, a 90% confidence interval, here minus 10% is not in this interval. So I am actually in this situation. My lower bound is minus 7%. So minus 10 is here. I reject the null hypothesis, so non-inferiority is stated in the situation. So that's how we do. It's important to remember that I have to correct my confidence interval so that if I want a 5% significance level here, I need to construct a 90% confidence interval. If I want a 1% significance level here, I would have to construct a 98% confidence interval, and so on. This is the last example, the choice of a 7 out of 8 unrelated donor. So this is also a bone marrow transplant data, and when we have unrelated donors, the researchers were interested to know the effects of HLA matching on unrelated donors. So if I have a 7 out of 8 donor, that means that out of 8 lucky, 7 were matched and only 1 was mismatched. So, and this mismatch can be in different locus. So basically here I have 4 groups. The locus where the mismatch was are different here for the donors in those groups, and here I have the number of patients in each of the groups, and the main question here is, well, does it matter where the mismatch is at or not? Is a better group here or not? And here I'm looking at the number of alive patients after 1 year. So in this example, there is not really a one standard or placebo treatment. I just want to know if being mismatched at A is equivalent to being mismatched at B, for example. So I'm not really, I just want to know if they are equal or not. So in this situation, what we call equivalent test is more appropriate. It's very similar to the non-inferiority test. However, my null hypothesis here now is that the 2 groups compared are different. And my alternative, the 2 groups compared are equivalent. Yes. In the non-inferiority test, the null hypothesis was one of the groups is inferior, is worse than the other. Here, they are different. And the alternative, they are equivalent. And my type 1 error would be to conclude the two treatments are equivalent when they are not, when they are different. And we state our hypothesis in terms of the differences between the two proportions. So I'm comparing two groups. Although the example have 4 groups, I'm showing you the test for comparing 2 groups. And our hypotheses are stated in terms of the difference of the proportions of alive patients. And I don't really care about the sign, if it's better or worse. So that's why I'm taking the absolute value. My null hypothesis, the difference, no matter to what sides, which one is better, is going to be greater or equal than delta. And here the difference is going to be smaller than delta. So here they are equivalent, here they are not equivalent. So those are my hypotheses. There are 2 ways, basically, of doing an equivalence test. One way, which is a more complicated one, not so complicated, but it's more difficult to explain, is to do 2 non-inferiority tests. So I will do 2 non-inferiority tests as I did before. I can do that. However, this is equivalent, completely equivalent to construct a confidence interval for the difference of proportions. The only important thing to remember here is that if I want to do an equivalence test, I need to correct my confidence level because I am actually doing 2 non-inferiority tests. So if I want to, for example, an equivalence test with 5% of probability of type 1 error, my confidence level is not going to be 95%, it's going to be 90%. I have to correct the confidence coefficient. And I construct the confidence interval as we are used to, the usual confidence intervals, and I look at the lower bound and upper bound. If I am in this situation, the null hypothesis is rejected. Remember, the null hypothesis is that they are different. So if the confidence interval is entirely within minus delta and delta, that means that the groups are close enough to 0 because I am constructing the confidence interval for the difference of proportions. So the groups are close enough to 0, and I reject the null, and I conclude that the groups are equivalent. If I am in this situation, here, minus delta and delta are in the interval, so I do not reject the null, because the groups may be different by more different than I would like they would be. If I am in this situation here, I also don't reject the null because one of the groups may be better or worse than others. So in this situation also delta is here, I don't reject the null. And similarly here, I don't reject the null. So what I did here, so we had 4 groups here, and they want to know if the locus, the donor and the patients were mismatched at is important or not. So I constructed confidence intervals for the difference of the proportions. So here it's the difference of proportions of alive patients mismatched at locus A and B. Here I am comparing A and C, here N and DRB1, and so on. So if you look at this confidence, the first confidence interval, we can see those are 90% confidence intervals. So I'm doing equivalence test with significance level equal to 5%. It's 1 minus 100 minus 9% divided by 2, but anyway. And if we look here, let's use the delta equal to 10% or 0.1. 0.1 is in this interval, so I don't reject the null. 0.1 is also here. I don't reject the null. If I look at A and DRB1, minus 0.1 is in this interval. I don't reject the null. This is the only situation that I reject the null. So I have evidence to conclude that B and C are equivalent, but not A and B, A and C, or A and DRB1. Those are not equivalent, only B and C. All other confidence intervals do not reject the null. When we do any test, hypothesis test, we are always worried about power. And for non-inferiority or equivalence testing, the power is a little bit different from what we have in usual hypothesis tests. And the power here is the likelihood that we correctly conclude the treatment is non-inferior or the treatment is equivalent when they are equivalent. So I want the probability of concluding the treatments are equivalent, given that they are in fact equivalent. I want that to be large. So I want a large power. And of course, if I have a large power, I would have a small type 2 error. And to compute the power, I need, of course, it's going to depend on my non-inferiority margin, delta, and also on the true difference of treatments. But if you look at the definition of power, it's the likelihood that I correctly conclude the treatment is equivalent when they are equivalent. So I can assume that they are equal. And with these assumptions, I can compute the sample size needed so that I would have I would test the hypothesis with a significance level of significance equal to alpha and a power equal to beta. So I can compute the sample size so that I have that level of significance and that power. So I have here the formulas for non-inferiority testing and the formulas for equivalence testing. And of course, for now, just don't worry about the formulas. I just want to show you that there are formulas and we can compute. And here I have for you, I computed some sample sizes for different values of delta, my equivalence or non-inferiority margins, and different values of the power. So as I told you, I want a large power, and we can see that the smaller the delta, the bigger the sample size I need. Larger power, bigger sample size, which makes sense. Okay, usually we need more people for equivalence tests, and if you look at these numbers, they are quite big. So this is a disadvantage of equivalence and non-inferiority testing. We need larger than usual sample sizes to have the same power with the same probability of type 1 error. Advantages are they are simple in concepts. It's kind of easy to understand. They are very simple to compute because I just need to construct the confidence intervals we are used to, just making sure I am doing the correct corrections on the confidence coefficients. So there are two advantages, but we need large sample sizes, and also we need to define the delta, which may be not easy. And there are some papers, for example, for binary outcomes. I showed here the tests for using the difference on the proportions, but you can state the hypothesis using odds ratios or different. There are some different ways of stating the hypothesis, and some researchers prefer using the odds ratios, for example, because they think it's easier to find a delta that has a clinical meaning. So it should have a clinical meaning. And also here I just showed the equivalence test and non-inferiority test for binary outcomes, because I really wanted to discuss the error with you, and what I really would like you is to understand why we switch the hypothesis and why it's important to switch the error I am controlling. So I can do these tests for survival outcomes, for some regression models as well, so we can do a little bit more than I showed here. And that's what I had to say. Thank you very much. And, if you have any questions.